So here you have your 5 phases: define, measure, analyze, improve, and control. And really those 5 phases form a funnel, as you see here. And my question is, why is this a funnel? What are we funneling here? Really, what are we trying to do in a Six Sigma project? Once we know how do we measure our practical problem that we are trying to tackle, what are we doing in the measure and analyze phase? Is really understanding what are the axes, the inputs that cause the variability that we are currently seeing in our Y, right? So really what we are funneling here, and then really what the tools that are integrated into this roadmap, into this funnel, help us is to reduce the axes to those 3 to 5 axes that really cause the majority of the variation in your Y. Those 3 to 5 axes, then we're going to take in the improvement phase and see, how do we have to manipulate those axes to manipulate the Y, which then, solves our practical problem or at least reduces it.
And we've got these 8 elements of waste. Toyota published 7. Another one's been added, the non-utilized talent, rearranged to spell downtime. Defects, not doing things right the first time. Overproduction, producing more than what's needed right now. Waiting, that's pretty self-explanatory. Not getting paid while you're standing there staring at space. Non-utilized talent, having talents, creativity, skills in your workers and your coworkers that are not being fully utilized. Transportation, movement of product or data files, because when things move, bad things happen. Inventory, like overproduction, but towards the beginning or in the middle of the process, things that are not needed yet. Motion, like transportation, but instead of movement of the thing, the product or the data file, this is the human motion. Stand up, sit down, think ergonomics. And extra processing is doing more than what needs to be done. Right? The excess approvals, the approval of the approval of the approval, the hand finishing, things like that.
So here you have the objective, metrics 1, metrics 2, metrics 3. So move the title of the metrics over here and then collect some baseline data. Again, last 30 days, 60 days, 90 days. That depends a little bit on how often do you measure these metrics. Could actually, obviously measure this for every single claim they're processing. Take actual data, look at your average over the last 30, 60, 90 days, and then the baseline is the average lead time it took for processing those claims in the recent past. And then you have your goal. And the goal is obviously where you want to be by the end of your project. And then again, you're looking at actual data and look at what was the best you were able to do? So in this case, what was the fastest we were able to do a process a claim? And here we say, hey, in average it takes us 4 days to process the claims, but best case is a day and a half. So we know that our process is capable to do it in a day and a half, but not consistently, right? And sometimes it's obviously much worse because our average in this case would be 4 days. That means, sometimes it may take 6, 7, 8, 10, 12 days. And so this is really a variation problem. Sometimes we can do it in the lead time we want, sometimes not. So that means we are here in Six Sigma, and we're going to try to understand what causes that variation. Okay, and then here the units actually is meant, what's the unit of this metric? So in this case, the units would all be days. I would even prefer to measure this in hours, right? So instead of just 1 day, 2 days, 3 days, go into hours, because then you see more variation, which makes it a little bit better or easier to understand what causes that variation. So this is the high-level process variables map. That is the first step for the process that you picked in your project charter. As I said, what goes in here is the name of the process, coffee making process. In this case, I have 2 Ys I try to improve. I have sometimes trouble that I have way too much coffee Sometimes I don't have enough coffee. So one why is that the quantity of coffee that I'm cooking. The other one is that the taste of the coffee. Sometimes my coffee is too weak, sometimes too strong, and sometimes it's just right. So those are the two whys that I pulled over from my project charter. And then I sat down with my wife and said, okay, what are some of the key inputs, right? Here I have my 6 M's. Do we have men? Yes, there's me making the coffee. Do we have machine? Yes, we have a coffee making machine. We also have a coffee filter. Do we have material? Yes, we have coffee powder. We have water. So again, high level, don't spend too much time on that. High level, what are some of those inputs? What I also like to do is I now take this process and actually go to step number 2, which means breaking down this process into some major process steps. And again, I told you it should be an ing word and a noun. So first step here is preparing the coffee machine. Then I'm going to add the coffee filter and the coffee powder into the coffee machine. I could have broken this down in 2 steps. I decided to leave it together. Then I'm going to add water to the coffee machine. Then I'm going to turn on the coffee machine. Then I'm going to wait, and when it's done, I'm going to pour coffee into my coffee cup or cups, and then I'm going to taste the coffee. Yeah. So that is my high-level process variables map. And that means this is what you would get after step 4. So here now they're rated. For example, the raw material vendor, we have different vendors. If we are changing from one vendor to another one, do we think as a result we're going to see sometimes cracks and sometimes not? They say it's moderate. No, different vendors. I can vary from one vendor to another one. I don't see any changes in the number of pinholes or surface defects. Here they see, what do we have, a big 9, a temperature, right? They say, the temperature is varying at the moment, and I think that is a big reason why we see sometimes cracks and sometimes not. It's a big reason why we see sometimes pinholes and not, and sometimes surface defects or not. How can this operator fail? That obviously would be one of those 16 human error modes. And one of those is excessive or insufficient repetition. That could actually happen here. In my process, that would mean he may add too much water or not enough water. So I have 2 different failure modes for this input. So I'm going to take one at a time, and I'm going to work them through. So first I'm going to take, adding too much water. Okay, if I'm adding too much water, then would I care? What are the effects? What are the potential effects of that failure mode? Hey, the coffee could be too weak, right? Or the coffee machine may overflow. If it overflows, it may cause an electrical shortage, right? And that may cause that the operator gets hurt. And that means I get fire in the kitchen. And that means I get in trouble with my wife. So all these are possible effects of that failure mode. They all go in one cell. Okay, and then for the first round, forget the severity. We're going to come to that in part 2. So don't do anything in the severity column. Now I started thinking about, okay, causes. Now why would an operator add too much water? So maybe there's no proper way to measure the correct way of or the amount of water. I have nothing in place, maybe. Or maybe there are no instructions available that determine, the proper amount. Okay, those are 2 causes, possible causes for this failure mode, adding too much water. Okay, what are the controls? What do I do to make sure that this cause doesn't happen? At the moment, I have nothing in place, and that's why I'm in trouble with my coffee making process. Also, I have no instruction, nothing in place, and so I give it a none there. How do I get a median of a data set? Now that depends. So if I have an odd number of data points, it's actually easy. I'm going to use the middle point. So you see here there are 4 to the left and 4 to the right, and there's 1 in the middle because we have an odd number of data points. So this middle one, that is called the median. So for the on-time shipment data, we have 9 data points. We take the middle one, and that is 90.8. and that's going to be the median of that data set. Now the question is, what are we going to do if we don't have an odd number of data points? So we don't really have a center. What we can do there, obviously we don't want to throw good information away. What we're going to do is we're going to do our dot plot again, and then we're going to look for the two that are in the middle. So here you see 4 to the left, 4 to the right, and then we have 2 in the middle. And then we're going to take the average of those two that are in the middle. That is called the median in the case you have an even number of data points.
If I hover over any of these entities, I will see that it is what the median value is, Q1, Q3, the IQ range, interquartile range. How far apart is Q1 from Q3? The whiskers that go down to the minimum, up to the minimum, and there was 24 data points. The more symmetric the box plot, the more symmetric the data. The more skewed or off-center the box plot, the more skewed or non-symmetric your data are. The thinner the box, the more tightly clustered the data are. The fatter the box, the more plateaued or thin or short and wide your data are. In this case, we've got two roles that we've looked at data for. I can use this to look for differences by role more easily than creating multiple histograms. Graph box plot with groups. Okay, I'll look at the brightness grouped by the roll number. What this does is it takes the data, it separates the data into group 1 and group 2, roll 1 and roll 2, and independently creates a box plot for each one and puts it on the same scale, so make it a fair comparison. So when we look at this, which roll has greater brightness on average? Roll 2. Clearly roll 2 seems to be in a higher place than roll 1. Do they have a difference in variability? We can compare the size of roll 1's box to roll 2's box. We might want to test for that because the graph, we might call it inconclusive. The way we interpret any and all control charts is that we take a look, are there any points outside the control limits? Yeah, we've got one. It even turned a nice bright red. The 1 means test 1. That's what it failed. We can hover on it and see that it came from observation 6, but we look for any points outside the control limits and any distinguishable patterns. Now, test 1's the only one that's turned on by default. To turn on the others, I'm just going to edit the last dialog, Control E or this quick button, or stat control charts, variable charts for individuals chart. Under the eye chart options is where we turn them on, turn them off. Eye chart options, there's a tab called tests. Here are the 8 Nelson run rules, the 8 run tests. By default, only test 1 is on. I can turn them on, turn them off as I want. I could use a pull down and turn them all on. I could use the pull down and say, just kidding, I don't want any of them. I could perform just selected tests. The reason why they're not all turned on all the time is if they're all turned on, there is a false alarm rate on any inspection. We'd have a false alarm rate of about 2%. 2% of our alarms would be false, just noise happening. In the upper right, we have by sample. In the upper right corner of that 6-pack is by sample. And what's done here for part 1, for cup 1, is all 6 measures, twice each by 3 operators. Those are the open circles. And the circle with the crosshair on top of it is the mean of all 6 measures. You probably don't see all 6 circles because we have some results that are identical and they sit right on top of each other. If all of the parts were identical, we would expect the means to all be the same and see a flat line going across. But these parts aren't the same. What we would like to see is the same amount of variability of measures around each part. So for example, when we take a look at part 2, we see pretty tight measures here. But we take a look at, for example, part 8, a lot more disagreement than we saw around part 2. Interesting. All right, we would like to see small spread, but similar amount for each one of them. Now, what Minitab's doing, or the math is doing, I want to say Minitab because any one of them would do it, is it looks at the variability of the means, the variability mean to mean. So of these circles with the crosshairs, it looks at that variation around, I'm marking a few of those. Let's say the mean is right through the middle here. So it looks at the variance from the mean off of each one of those. The more in control the process, the better. I am a little bit concerned that I see some out of control points. I'm a little bit concerned that I see a sawtooth pattern in here, but pretend you never saw that. I want roughly normal data. Pretend you didn't notice the 0.03 was less than 0.05. It's close, it's close. But here's on the 6-pack, we can judge stability. We can judge normality. And we get a histogram with the fit, with the curve sitting over it. And we can see how well it fits into the spec limits. We can see that this process won't fit into those specs even if it had to. It's too fat. And because it's too fat, the potential is going to be no good. We look down here, CP 0.43, PP 0.33. That's terrible. Six Sigma quality level is a CP or a PP of at least 2. We see that it's off center. It's shifted to the right. That tells us that the current performance will be less than the potential because we didn't park down the middle of the parking spot. So CPK 0.19 compared to 0.43, PPK 0.15 compared to 0.33. The current performance is lower than the potential because it's off center. 6-pack has a lot of stuff, control chart, normality chart, histogram, capability plots. This 2-sample T for Y equals the amount. We have a summary table of that there were 50 of each, what the sample mean was, the sample standard deviation, SE of the mean, standard error of the mean, the uncertainty of the mean given the size of the sample and the variability of the sample. The difference, mu of Fred minus mu of Sue. Right? Okay, as long as we're looking at equality versus inequality, the order doesn't matter. Estimate for the difference, well, 26.95 minus 24.596 would give us 2358. Once we go to those decimal points. Console for the difference. Best and worst case. We're saying best and worst case, that difference is somewhere between 1.9 and I'll round that to 2.8. Fred minus Sue is somewhere between 1.9 and 2.8. Notice that 0 is not one of your possibilities. 0 is not in the range of 1.9 to 2.7. And if the difference is definitely not 0, that happens if and only if the two means are definitely not the same. Compsonal approach. T-test for the difference, equal 0 versus not equal. We have this T value. There's your test statistic calculated. Meaningless to you unless you have a T distribution and knowledge on how to use it. But we have our P value. The P value, 0.000. Now, easy question. All you got to ask yourself, is that above or below 0.05? The response is the predicted is the shear strength. The predictor is the age of the propellant. We're only looking at linear models here. We're not going further. And that's what we want to take a look at. So we choose OK. And here is our scatter plot and the best fit line that can go into it. So we believe that as this got older, it lost strength. We've got a graph without even using the equation. The graph confirms our business belief that, yes, as this gets older, it's getting weaker. It's losing its shear strength, and that's not a good thing. So we have the equation of the line sitting right across the top. It tells us the best guess that we have is that the shear strength can be predicted as 2628 PSI minus 37.15 times how many weeks old it is. So for every week this solid rocket fuel ages, it's going down 37 pounds per square inch PSI in the shear strength. So we could then calculate, we could put in how strong would it be at 10? How strong would it be at 20? We could plug in 10 and 20 and solve it. And while we do see that St. Louis had the most early deliveries out of everybody, does that make them any better? You know, if we just did that raw pivot table, we'd be all over St. Louis for having the most early. But then again, they also had the most late at 6. Miami had the fewest late at only 1. Yay, Miami. Or as they say, they're Miami. But is it enough to be of any kind of importance? Well, we look at Pearson's chi-square, 2.4. Degrees of freedom, 4. This is a 3 by 3 table, so 2 times 2. That p-value, though, 0.662. Not statistically significant. There's no significant difference between the observed and the expected. So any differences here at the cellular level could just be luck of the week, luck of the draw, sampling error, sampling uncertainty, sampling variability. And this effects Pareto is a brilliant graph. It is so easy to present in public. It's awesome. We take a look at this effects Pareto, and it says how large is that effect. So we look at it and say the largest effect is factor A, is temperature. Going down, the next largest effect is the interaction. Least of the large effects is B, pH. And this red line that was calculated and put on here, what that indicates is any effect, rather, that crosses that red line is statistically significant at the 0.05 level, the level that we've been using. So if it crosses the red line, and they all do, they are statistically significant. If it did not cross the red line, it would not be statistically significant, and we could remove it from the model. So instead of looking at p-values and showing a bunch of numbers to our audience, here is the result from our study, and we found that temperature, that everything does affect brittleness, and temperature, look at that, so much more than everything else. Temperature is our leading effect of what changes brittleness as we change temperature from low to high, from 200 to 350. Taking that a step further, that target value, that's a form of poka-yoke, mistake proofing. Line up the lines. What do we need to do? We need to set the line, set the arrow to the line. It only needs to be done once. Fix it and forget it. And the press operator needs to do that, and it needs to be done by the middle of February. Periodically, we can go out and we can measure, which is a form of inspection, and that's going to be done monthly. And that's the job of the maintenance department. That's going to be done starting the end of February. Meanwhile, we're also going to audit. We're going to periodically check to make sure that these inspections are being done. So we have a checklist, which is an audit form. So the press supervisor, once a quarter, goes to make sure that the maintenance log is completely filled out and sign off on it to inspect the inspector. And they're going to start at the end of Q1. So maintenance signs off once a month, and once a quarter, the press supervisor makes sure that maintenance signed off every month.